In this video, we're going to look at and discuss the difference between constant pressure work and variable pressure work. There are two types of work that typically you encounter in general chemistry, constant pressure and variable pressure, and it's important to look at the differences, the similarities, and to see how use of the wrong interpretation of work can lead to the underestimation or the overestimation of a result. Okay. So first of all, we'll consider constant pressure work. Now, because we're looking at constant pressure work, it's assumed that we're looking at an ideal gas. So that consider expansion or contraction of the ideal gas against a constant pressure, external pressure. So constant pressure work is W, is minus pressure, change in volume. So here, I'm assuming that D is change. You can use a triangle if you like. I'm going to use them interchangeably. So minus pressure by the change in volume. If we look at plots of pressure and volume, so pressure against volume, so let's call this A. Let's do it again. Plot of pressure against volume. Let's call this B. Okay, so I've got two plots of pressure against volume, A and B. Well, typically we say that the work done by the system is the area under that curve. So if I look at the area under this curve, so I'll do a dashed line under the curve. If I look at that area, then the area under the curve is work. So I'm going to say that the shaded area under curve is the work. Okay, so it's that value W, or at least it's supposed to be. The problem is, this is the constant pressure work. Now here we can clearly see the pressure is changing. So what I've actually, if I use this equation, because I don't have a D on the P value, what I'm actually going to do, I'm going to start with this initial value and I'm going to overestimate by this much. So all of this material clearly is an extra area. So if we look at the graph I've labeled A here, let's say we've gone this way. Let's say I'm reading it left to right. So I'll put an arrow here, I'm reading it left to right. So this is my initial pressure, that's my final pressure. Well, this is going to be essentially an expansion. So this would be expansion. Because I'm increasing my volume. So it leads to an overestimation of the expansion work and that overestimation is what I've shaded with parallel lines. Okay. So I really only want to calculate the actual work done during this expansion. I only want the area shaded here. But because I don't have the ability in my constant pressure work equation to vary the pressure, it actually overestimates by this much, and I get a value larger than I should have. If I look at the graph I've labeled B, again, I want the area under the curve. If I'm going to go that way, this would be a compression. So I'm going from a higher volume to a lower volume. The work done, if I do it correctly, would just be the area under that curve. But, again, because I don't have the ability to vary pressure in my equation, I'm actually just going to measure the horizontal value. Here. And in fact, if I shade it slightly differently, let's see. My error, I guess, is going to be this value. So that's going to be my error. So I'm only going to measure the shaded region if I use the wrong equation. So in this case, I'm going to underestimate because I'm not going to account for the change over here. Again, I'm assuming that during the start, the pressure doesn't change, so I overestimate. I'm assuming here at the start, my pressure doesn't change, so I'm going to underestimate. So I'm going to underestimate. Well, there's going to be an underestimation of the compression work. And that underestimation is the area, again, I've shaded with horizontal lines. So again, just to recap, what we're concerned about here, we're looking at constant pressure work, or the constant pressure work equation. Work is the negative of constant pressure by the change in volume. We can look at two scenarios, expansion and compression. So if I look at this plot of pressure against volume, and I start at a high pressure, relatively low volume, and I go that way, because I'm using the constant pressure equation, there's no way to incorporate the change in pressure, so the equation assumes a constant pressure during the volume change. So when I come to calculate the area under the curve, it overestimates by this much. So I overestimate the expansion work done, so I get a larger than actual value. Conversely, when I look at compression, I'm starting over here and I'm going that way. So I'm going from a relatively large volume and low pressure to a relatively high pressure and low volume. But again, the equation can't accommodate the change in pressure. So it assumes that the pressure from the beginning doesn't change, and it underestimates all of this area, which represents work done during the compression. So I underestimate the work of compression, I get a lower than actual value. So clearly this is not great. This is, however, how you would calculate constant pressure work, and I believe that we've looked at examples of this already. An example of a constant pressure system would be so for example, if pressure is force over area, So when you're applying a fixed force to a given area, so let's say a gas is doing work against a piston and the piston has a mass on it, and that mass doesn't change. It applies a constant force on the piston, then that would be a system in which the pressure is constant. And you could use work is minus PdV. Let's look at the other option. So I'm going to erase all of this. And we'll see the origin of the variable pressure equation, which we haven't yet looked at. So this is our variable pressure work. We take a plot of pressure against volume. We'll take our same curve. What we really want to do is to look at slices and add those slices together. So we want to look at small slices best we can and then add them together. So this tells us how to solve the problem. We know that the work is negative by definition, but I now want to sum these pieces together. So I use Newton's old way of writing S. This is an Old English S. Most people now know it as an integration, but integration just means sum, and the symbol comes from the 1600s in England. I want to sum between a final value of volume and an initial value of volume. So 2 just means final, because the number 2 literally comes after the number 1. PdV. So this means that I want to look at the work summed between final and initial conditions. When a pressure is applied, the pressure which causes a change in volume. Okay. We're also going to assume the pressure here is an ideal gas, so it's equal to nRT over volume. So we're going to use our ideal gas equation. So this implies that work, if we now replace P with nRT over V, so it's minus the sum between a final volume and an initial volume of nRT 1 over V dV. And the sum, we're only summing over differences, right? So this is a difference. Each one of these is a dV. Next one is also a dV. So we're only summing over changes in volume. We're not summing moles, we're not summing R, we're not summing T. So just to clear up so that the sum has direct access to the thing that it's summing over, it's a convention to take the constants that don't apply to the sum to the left side of the sum. So we can rewrite this as minus nRT sum between final and an initial volume 1 over V dV. So I have to keep the 1 over V to the right of the sum because I'm summing over volume changes, so anything with a volume sensitivity has to be incorporated by the sum. Now there's a rule that says when you sum 1 over a variable x as x itself changes, so x can be anything, by definition, it equals log x. Okay. Then we can apply that to our case here. So we have work is minus nRT, and then I apply the log to both the final and initial volume. So it's going to be log V2 minus log V1. And I can rewrite the difference of logs as the fraction of the log ratio. So I've got work, now my variable pressure work, is minus nRT log and then the ratio of volumes. So that's my new equation. And again, this is the equation that's the variable pressure work, because it's constantly looking at the ratio of volumes caused by the pressure. Okay, and this would result in, instead of an overestimation, this would literally just look at the area under the curve. So we've got neither an overestimation of expansion nor an underestimation of compression. So neither an overestimation of expansion nor an underestimation of compression. Okay. I'm just going to... Okay. So let's try a problem with that then. Let's actually plug some numbers in and see if we can calculate something. Okay, so we'll erase this. Actually, I don't have an example here. Yeah, I actually don't have an example here. So we won't do an example of that, but you should have examples that you're looking at. More importantly than the examples, though, is the difference between the equations, and definitely I would expect that you can see the difference between the equations and see how one of them incorporates the change in pressure and one of them doesn't, and when to use the right equation and when not to use the right and when to use the other equation that then becomes right. And to be able to annotate a graph on the expansion overestimation of work and the compression underestimation of work. So I want to alert you to that. The final thing I would like to look at in this video is something that comes up under adiabatic conditions and isothermal conditions. Okay. So I'm going to erase this. and I'm going to call this adiabatic versus isothermal expansions. Okay, so we've just had a look at constant pressure work and variable pressure work. Now we're going to focus on this type of change work, however you want to quantify the change, under two different set of conditions that can lead to wildly different answers. And I want to draw your attention to this. I think it's important. The comparison of isothermal and adiabatic. So adiabatic, we mean there's no change in heat during the process. Isothermal, there's no change in temperature during the process. And it has consequences, and I think we should look at those consequences. First of all, let's look at the graph. I think this will be the most informative way to begin. If we look at this expansion because the volume is increasing, going from left to right, this would be the isothermal, or let's state that this is the isothermal expansion. Isothermal just means that the change in temperature is zero, so there's no change in temperature during this process. The same expansion under adiabatic conditions would be a more steeper slope. This would be adiabatic, and this means that the change in heat, most people call the change in heat just heat for reasons that we won't go into, but the heat component is zero. So we want to look at the difference, because if we had to calculate the volume change and we use the wrong set of equations, we get clearly the wrong answer. So we want to try and understand why the adiabatic conditions would clearly differ the work done if we calculated work compared to the isothermal conditions. Okay, so let's focus on the adiabatic, because that's the unusual one. We're going to reiterate the first law of thermodynamics. Which says that the change in internal energy is the sum of heat and work. And under adiabatic conditions, heat is zero. So heat is zero under adiabatic conditions. So this means that the change in internal energy is just work. Okay. For an ideal gas, internal energy depends only on temperature. So to reiterate an equation we've already looked at, we know that a change in internal energy, and here I'm assuming that the delta and the D can be used interchangeably. This is just going to be a quantity, let's say moles, constant volume, specific heat, and a change in temperature. Okay, where here N is mole. You could use mass. It really doesn't matter. This could be heat capacity per mole. So then you scale it to moles, and this is obviously the temperature change. We're also going to look at our previous equation for constant pressure work. So we know for an ideal gas, these two statements are true under certain conditions. But since we have adiabatic conditions, in which change in internal energy is work. So since we have adiabatic conditions where the change in internal energy is work, we can set these equal to each other. So we can say that N molar heat capacity change in temperature is just equal to work, where work is negative P change in temperature. Sorry, change in volume. Okay. So this is just du equals W. Okay. I'm going to keep the graph. I need to erase some stuff because I'm almost at the end of my board. But the great thing about a video is you can pause it and copy what you need to. So I'm going to erase this bit here and keep going. So if the process is reversible, then we can say that pressure is nRT over V, so the ideal equation of state. And if that's true, then our previous statement that the moles times by the molar specific heat molar heat capacity at constant volume, or delta U, is equal to work, which is minus, remember, work is minus P delta V. So that's minus nRT over V dV. So again, this expression here, remember, was du, which is equal to work. Work is minus P dV, so, and P is nRT over V. Okay, so you can start to cluster those together. Now we're going to divide through by NT. So we're going to divide by NT. Why would you do that? Typically, historically, people try a lot of things and you tend to hear about things that were useful. So there's no need a priori to know why you would do it. Because that's not how the people do it. They try a bunch of stuff and they follow the leads that lead to new knowledge. And if you're lucky enough to divide by NT early on, you get to new knowledge quicker. If you don't realize for a long time that dividing by NT leads to new knowledge, then you're going to be there a bit longer. Okay, so we only know what works. Dividing by NT is useful, so let's have a look. So we've got N CV dt over NT. We've got minus nRT over V dV multiplied by divided by NT. So I'm dividing both sides by NT. And we can see that the N cancels here. And we can see that the N cancels here. And the T cancels here. So we're left with CV dt over T is minus R dV over V. So this is nice because we've got one denominator, and we've got two constants. CV is a constant, change in temperature over itself. R is a constant, change in volume over itself. So it just looks nice. It looks like it's a good looking equation. Okay, we're now going to follow through the consequence and see where it leads us. So I'm going to erase this board. Now I will need to erase the graph. Okay. So previously we just saw that CV, I'll rewrite it slightly, 1 over T dV, dt, is minus R 1 over V dV. That's what we had previously, rewritten in a slightly different way. And recall that I want to, well, I've got this 1 over x dx. I'm eventually going to put logs in there because of that rule earlier on in this video. So this implies, but before I do that, I've got to sum over the changes. So the way to get rid of the changes is to sum over them. So I've got CV summing between a final temperature and an initial temperature, 1 over T dt is equal to negative R summed over a final volume and an initial volume, 1 over volume dV. Okay, again, why am I summing? Because I'm summing over all the changes. The sum of the changes is the whole. So basically I took an object, divided it into an infinitesimal number of bits, and now I'm going to reconstruct those bits to get back to the whole again. So this implies that CV log T2 over T1. Again, earlier in the video I showed you how why this is the case, is equal to negative R log V2 over V1. Okay, so we've summed over the changes and got rid of them. We know from our log rule, if I change the sign of the log, I log the inverse argument. So this is equal to positive R log V1 over V2. Again, if I change the fraction here, I change the sign of the log. Okay, so we've got everything positive. So let's rephrase what we have. So we have log T2 over T1 raised to the CV. Remember from your log courses, you can write a log expression where the exponent is either an exponent or a coefficient. So if I have a coefficient CV, I can rewrite it as an exponent. That's just one of the things we can do with logs. Equals log V1 over V2. So I'm looking at this one over here. And again, I've got a coefficient, so I can write it as an exponent. So log V1 over V2 to the R. Now recall something we've looked at previously. So recall that CP is CV plus R. So we already looked at that earlier on. We're just going to restate it again here. Well, this implies that R is CP minus CV, so we just take CV to the other side. And we're going to sub in this way of looking at R into into this equation here. Okay, so we've got log, well actually we don't need the log anymore, right? We're going to take base exponents of both sides, so this is log base e. Let's hit both sides with an exponential, so we can just write t2 over t1 to the CV is equal to v1 over v2 to the r, where r is now Cp minus Cv. Okay. If I want to get all the exponents on the same side, then I can divide both sides by Cv, or I can take the Cvth root of both sides, I guess. So if I were to put Cv here and Cv here, okay, so take the Cvth root of both sides, then I have T2 over T1 is equal to V1 over V2 Cp over Cv, and then Cv over itself becomes 1. So I have T2 over T1 equals V1 over V2 to the complicated exponent Cp over Cv minus 1. That Cp over Cv, let's call it gamma. So let the ratio of constant pressure, heat capacity, and constant volume heat capacity equal gamma. So this is the way it's typically abbreviated. So then I've got T2 over T1 is V1 over V2. Remember, T is temperature in Kelvin, V is volume in whatever unit is relevant to you, to the gamma minus 1. Okay, we've just rephrased Cp over Cv as gamma, just for convenience. And I can rewrite this by bringing the V2 up here and the T1 up there. So I can rewrite this as T1 V1, where V1 has the gamma, so it's the gamma minus 1 is equal to T2 V2 to the gamma minus 1. So this is an equation I would expect that you know. It'll be useful, or I'm telling you that, hey, this is important moving forward. So let's call that equation 1. I'm going to have to erase something, and we're almost done providing the big equation, which is going to come next. But I need a bit more board space to do it. So we're going to erase this real quick and look at our next equation. We're going to rewrite that at the beginning now. So let's erase this. So we'll start off with T1 V1 to the gamma minus 1 is T2 V2 to the gamma minus 1. We call that equation 1. That's what we had previously. Recall from gases the combined gas law. So recall the combined gas equation, which is P1 V1 over T1 is P2 V2 over T2. So this is the combined gas equation. Let's call this equation 2, just in terms of labeling it. So now we're going to multiply equation 1 by equation 2. So we're going to multiply 1 and 2. That's what we're going to do. Okay. So let's do that. So we're going to have P1 V1 over T1. That's the part from 2, and then the part from 1 is T1 V1 to the gamma minus 1. And then we've got P2 V2 over T2. And then from equation 1, we have T2 V2 to the gamma minus 1. Okay. We can cancel the T's immediately. They go. So T1 and T2 are both numerator and denominator, so they can cancel. And then if we look at how the V's behave, then we've got a product of V1, the regular V1, and then V1 with this condition, this gamma minus 1. And then likewise on this side, V2 multiplied by V2 with conditions. Let's divide both sides by V1 and V2 respectively. Actually, no, let's not do that. Let's consider what this actually means. We've got V1 multiplied by V1 to the gamma, and then again to the negative 1. So let's see. Since V1 to the gamma minus 1 multiplied by V1, okay, which is what we have, equals V1 to the gamma V1. So the gamma is just the gamma, so V1 to the gamma multiplied by V is V1 to the gamma multiplied by V. But then we've got V1 to the minus 1. Well, that's just 1 over V1. Right? So again, the way to interpret this, V1 to the gamma minus 1 is V1 to the gamma, which is V1 to the gamma, multiplied by V1, which is there. And then V1 to the minus 1, well, anything to the minus 1 is 1 over. So it's just 1 over V1. So the V1s cancel, and I'm left with just V1 to the gamma. So because of that way of looking at what this product actually means, then we know that we're just left with, when the V1 hits the V1 gamma minus 1, we're just left with V1 gamma. So we're left with P1 V1 gamma. We do the same on the other side. P2 V2 gamma. Notice that's an adiabatic variation on Boyle's law. So this is our adiabatic variation on Boyle's law. Remember, Boyle's law just said that P1 V1 is P2 V2. So this is different. We have this extra consideration here because it's adiabatic. We don't have that consideration there. Boyle's law is our isothermal variation. This one with the gamma is our adiabatic variation. Okay, let's see how you would actually use this in a calculation. Okay, the question just says, I'll read the question out, I won't write it down. It says 5 mole of an ideal gas, a monatomic gas, at an initial temperature of 298 Kelvin and a pressure of 10 atmospheres is expanded adiabatically and reversibly until the pressure has decreased to 1 atmosphere. Calculate the final volume and temperature, calculate the energy and the enthalpy changes, and calculate the work done. Okay, so here's the answer to the question I've just read. Let the initial volume V1 equal nRT1 over P1. So we're just using the ideal gas law, and we're saying initial, so we've got the subscript 1 where it applies. So it applies to volume, pressure, and temperature. So we've got V1 is our initial moles, N, so 5 mole. R is 0.08206 liter atmosphere reciprocal mole reciprocal Kelvin. T1 is 298 Kelvin. And P1 is 10 atmospheres. Okay, and we calculate that to be 12.226 liter. We're only good to 3 sig figs. We're just propagating a few extra digits here. Let's look at gamma. We know we have to look at gamma because we're told we're under adiabatic conditions. So let's see how to handle gamma. Recall gamma is a ratio of Cp over Cv. And recall Cp is 5 over 2 multiples of R, and Cv is 3 over 2 multiples of R. So this is just the constant 5 over 3. Okay, so that's how you incorporate gamma. We know from our adiabatic process, we know that P1 V1 gamma is P2 V2 gamma. So we know that therefore V2 gamma is P1 over P2 V1 gamma. So we know that V2 gamma is P1, which is 10 atmospheres, P2 is 1 atmosphere, and V1 is our answer here, so it's 12.226 liter. So our atmospheres cancel, and we have, well, first of all, this is equal to V2 to the 5/3 power, right? This is V2 gamma, which is V2 to the 5/3 power. But I just want V2. I just want V2. I don't want V2 to the 5/3 power. So this is just going to be, well, actually, let's see what this would be. I didn't calculate this. Let's see what it would be. This is 10, well, it's 10 multiplied by that. So this would be 122.26 liter. So that's an overestimation of what I need. Okay. So I know that V2 is just equal to, well, I need to take the gamma over to the other side. So this is 122.26 liter. So to undo the gamma, I've got to take inverse gamma of both sides. So I just flip what gamma means. So instead of 5.3, take it to the 3.5. So V2 would equal 48.7 liter. Okay. Okay, so notice you won't get the right V2 if you don't incorporate the gamma. So it's very important that we look at adiabatic conditions. That was volume. Let's look now at the temperature. So temperature, final temperature is P2 V2 over NR. So again, we're using the ideal gas equation, and we're labeling it with 2 for final. This equals the final pressure of 1 atmosphere. Our V2 that we just calculated, 48.6. I'll give the extra couple of digits. N is 5 mole. R is 0.08206 liter atmosphere reciprocal mole reciprocal Kelvin. And this implies that our final temperature is 118.62, so 119 Kelvin. Okay, it has to be in Kelvin. Recall that delta U is W because we're under adiabatic conditions. And recall that delta U is equal to N CV delta T, which is equal to 5 mole. CV, we know that CV is 3 over 2 R. So 3 over 2 R, we have to switch now to the value of R with energy units. So 8.315 joule per mole per Kelvin. So we have to use the appropriate value of R. And then delta T is final minus initial. So it's 119 Kelvin minus the initial value of 298 Kelvin. So that's our temperature change, which equals, so we've got work equals negative 11,162. So about negative 11,200 joules. We're only good for 3 sig figs because of our 5.00. So the first non-significant digit adds 1 to that 1. And we're only allowed to report 3 sig figs. And then finally the enthalpy. Enthalpy is equal to NCP delta T. So compare and contrast this. The internal energy is constant volume, molar heat capacity. The enthalpy is constant pressure, molar heat capacity. So this is just going to be 5 moles. CP, recall, is 5 over 2 lots of R. R is 8.315 joule per mole per Kelvin. Final temperature minus initial temperature, 119 Kelvin minus 298 Kelvin. So the enthalpy change is negative 18,000 604 joules. We only get for 3 sig figs, so it's about 18,600 joules. Okay, we are coming up to the hour, and that will soon conclude our video. So just to summarize what we've looked at, in this video, we started off drawing our attention to constant pressure versus variable pressure work, the consequences of overestimating expansion work or underestimating compression work. Then we shifted most recently in these videos to the slight adjustment to Boyle's law, specifically Boyle's law, when we have an adiabatic environment versus an isothermal environment. Boyle's law, P1V1 is P2V2, applies under isothermal conditions, and you can look at obviously the area under a curve under isothermal conditions and calculate work and what have you. But under adiabatic conditions, you have this feature that changes. You shift from constant pressure to constant temperature, pressure to constant volume conditions, and you have an adjustment to the area under the pressure volume curve. That will lead to a need to adjust the calculations that you do, and we have this factor of a gamma, which is the ratio of Cp over Cv that we have to incorporate. So again, we've compared two situations, isothermal and adiabatic, and how it can impact work calculations and most recently pressure calculations. And that will conclude this video.